thanks for the introduction, Olivia. Also, welcome from my side. So, my name is Natalie Vollert, as Olivia already mentioned. And today I'm going to talk about a project, one of our most recent projects. It was just finished a few weeks ago, where the problem was the classification of documents in an industrial environment. And I'll show you how we solved that using natural language processing. So maybe a few words about the agenda, so what I'm going to tell you today. So first of all, we're going to start with the problem definition, so document classification. Why is this even important? Why is it useful? Then I'll give you a quick overview of NLP text classification in a nutshell, so what are the methods that are used to accomplish this. Then I talk a bit about the use case of the project we were working on, and if there is time left, I'm not sure about it to be honest, I'll also give you a short overview about the tools we used and how we implemented this. So document classification, why is this an important topic? So during the last years, many companies, or I guess most companies, were in digitalization processes. And one part of this is often to really get rid of printed documents. So you somehow want to digitalize them, to use them for modeling, for instance, for modeling or for any other processes. So imagine you're a big company, you're having like hundreds, thousands, or millions of documents. So it's really necessary that you somehow tag them with some information, with some metadata or something like that, just to find them again, or find information that you need. And yes, as far as we know, this process is very often done manually. So what does this mean? So I'll check if this works. Yeah, that's great. Okay, so we are here on this side of the graph. So what's happening? The documents are coming in, and then there's a group of people, a group of experts who are really classifying those documents or tagging them with information manually. This basically means they are opening them, searching for information, and giving them the metadata, the tags that are needed. And so the question was, couldn't this be done much easier by using an AI-based approach? Because it is really realistic that you can assume that you save up to 70–80% of resources, meaning especially time and money, if a computer is doing that instead of a human person. So the answer is yes, it can be possible, and we solve this by using NLP-based methods. So what are the things to note besides that? So first of all, as I already mentioned, this digitalization process, they are already happening for a few years. So you usually have labeled data, that's a good thing. So we're talking about supervised learning here. And how is this looking now? So now we are at this part of the graph. So what should happen? The documents are still coming in, but then the first thing that happens is you have your AI that more or less takes them and tries to classify most of these documents. Of course, there will always be some documents left that the AI either cannot classify because it just doesn't know this sort of document, or where the probability is just too low, so you're too unsure. So you still need the experts that just control the output of the AI, more or less. I think that's a very important point, because the goal of this project was not to really replace the team of experts, but to support them, to make their workflow easier and faster, just that they can think about, let's say, more important things. And also one side effect that's really nice to note is you also increase your data quality. So why is that happening? Imagine you're the person who's sitting 8 hours a day tagging documents, so you will get tired and you will make errors, and an AI simply doesn't get tired. So you can also, so the amount of documents that still have to be classified by humans is just much lower, so also your data quality is increased. So text classification, I already said the text classification was the way to go here for us, and what does this mean? So this approach, it's a subfield of NLP, and it just has the goal of classifying texts in some predefined categories. So in our case, we try to classify documents. We want to group them, for instance, by their topic, by their document type, their legal form, whatever. There are many different possibilities for that. And the challenge is, of course, that human language is not really defined by a clear set of rules that you simply can fit into a model and then everything works. So first of all, you really have to think, okay, how can I even generate my features that this even works? And there are basically 3 main steps for this. So first of all, you're doing some text pre-processing. Afterwards, you're generating your features based on this pre-processed text. And then, of course, there's the training of the ML models, of the machine learning models left. And I'll just give you a very quick overview about all of these 3 steps and what we basically did there. So the pre-processing. So imagine you're getting some sort of document. Of course, there's a lot of uninformative and unnecessary parts in it. This can be things like blank rows or some special characters or things like that. So the first thing you're doing is some sort of character filtering. This could be something like, first of all, remove all of the unnecessary spacing that's in the document, remove, for instance, non-alpha text, and also for the German language, put everything to lowercase. So the last 2 points, especially this non-alpha text and the change to lowercase, does really depend on the sort of problem you're working on, because there can be fields where it's important if it's a lowercase or an uppercase, or where you're interested in Greek letters or whatever. So you just filter out the characters that are not important for your problem. The second step would be to remove so-called stop words. So what are stop words? Those are basically words that are quite often used in a language, but they give you no information. Like in the German language, a good example are articles. So you don't really need them. It's not important to keep them in your texts. And the last step in this pre-processing would be the so-called stemming. This just means that you reduce all the words to their word stem, just to make the number of words that are in your text a little bit lower. And once you have those cleaned texts, so they are not really readable anymore, you can go on with the feature generation. So what's the first thing you do? So the first thing is the so-called tokenization. This just means that you break your text into meaningful chunks. This can be words, or it can be a group of words. In our case, it were simply words. So each token was 1 word. And then the simplest way to generate features is the so-called bag of words. This just means that each word that is in your text is a feature. Each document you have is a sample, and the values are just the count of the words in each document. It's basically as simple as that. But what happens, of course, is you give a higher weight to longer documents. That's something you usually don't want to have. At least we didn't want to have that. So what you do is you use frequencies instead of that. There are basically 2 possibilities what you can do here. The first one are so-called term frequency features. This just means that these word frequencies are divided by the word counts of the document. And the more sophisticated method, which just further reduces the weightage, are the so-called TF-IDF features, so term frequency inverse document frequency features. Here you also multiply the TF features with the inverse document frequency. And this was also the way that we were generating our features in the model that we built here. So and once you have your features, or once your features that is done, you of course will go on with the modeling. So if you start looking in the text classification literature, there are basically 3 models that you will most often encounter. So it's naive-Bayes, it's support vector machines, and it's neural networks. And basically that's also, I'd say, the order of complexity. So usually you would start with trying naive-Bayes. If this already works for your problem, I think you're lucky, because it's fast, it's simple, it can work very well. It didn't work in our case. So we had to go on and switch to support vector machines, and gladly they gave us really, really good results. So as time is very short, I won't give too much detail about support vector machines. Just as a short reminder, what they basically do is they just search for the best hyperplane that separates the data into the categories. And you basically can either use linear or non-linear support vector machines. That's an important thing, because usually non-linear support vector machines are the more flexible ones. And you may think, okay, this problem seems to be quite complicated. Let's get with non-linear support vector machines. Shouldn't do that, in fact, because you're having so many features. Imagine each word is a feature. So we're talking about like 100,000 or more features. And non-linear kernels really tend to overfit the data. So just try to keep it simple, use linear kernels instead, and that's basically what we did. So we used TF-IDF features and linear support vector machines. And then there's one thing, I will not go into too much detail on this slide because not all of it is important. It's just something that we learned in a lot of projects and also in this project. So the main message is use expert knowledge whenever you can, because there are people who did this by hand for many, many years, and often they have something like, let's say, a list of rules that they apply. So sometimes they don't even have to open a document. They just see the name of the document. Okay, I know it's class A or it's class B. That's really something you should use, and we also did that. So we also introduced or enriched our model, our SVM model, with some expert knowledge. And in fact, this improved our model by around 10%. So it was really, really helpful to also do this and use some of these, thank you, some of these hard-coded rules also. And now I'll give you a bit of information about the use case. Of course, I cannot tell you too much because it's confidential, but nevertheless, I can give you an overview or tell you what was achieved at this problem. So the project itself was done in cooperation with BASF. That's a big company in the chemical industry. So we're talking here about the classification of chemical industry document. That's important to note, I think, because they have, of course, a very specific vocabulary. So this model will not fit to any other problem, but it's really specific to the documents that they were having. So they have done a lot of work within the last years. So we had a lot of data already. In fact, we had about, I don't know, 2 million train data and 700K for testing. And they had a lot of categories. Actually, it was 200 predefined categories that they wanted the documents to be classified in. So our workflow was really the workflow that I described in the last slides. So we pre-processed the texts, we used the TF-IDF features, we used our linear support vector machines, and this gave us an accuracy of 90% of the documents that were categorized in the right class, which, to be honest, was a bit more than we expected. So we had a goal of 80%, and we're very happy that we can made it up to 90%. So the thing was, okay, after we finished this modeling, the question of the client was like, okay, so is it possible that we somehow identify at least part of these documents that are not classified in the right class? Because it sounds a bit weird if you say, okay, every 10th document gets the wrong tag, so it still sounds much. And so we said, yeah, of course we can do this, because what we get is we get probabilities for each document that's assigned to a certain class. And so we use these probabilities and searched for a threshold to say, okay, you have a document, it's classified into a class, and if the probability for this classification is below a certain threshold, give the feedback to the user, please classify this document manually, because we are simply not sure if that's the right class to use. So what you can see at this upper graph is basically how these three possibilities you have now for a document, so it can be true, it can be false, or you have to classify it manually, how this looks if you change this threshold. So of course, the higher the threshold is, the more documents you have to classify manually, and the lower gets the rate of false classified documents. But you also don't want to have too many documents that have to be classified by hand, so it was a bit of finding a good balance here. And what we finally did, or what we agreed on, was, okay, we're setting the threshold in a way that 88% of the documents are just classified in the right class, according to our test data at least. 5% are still false, because I think you cannot avoid that totally. That's simply not possible. And for 7%, more or less, the user gets the feedback, please look at this document and classify it by hand. And the second graph basically just shows why this is working. This gives you the histograms of the probabilities of documents that are classified in the right class, which is the dark one, or in the wrong class, which is the pale one you can see here. And as you can see, the probabilities for documents that are classified in the wrong class are generally quite low. So that's also the reason why the threshold worked very well. So, and finally, I already see that time is running out, so I will just tell you the important facts of this slide. So actually, this was a really I'd say beautiful data science project, because there were so many different parts of data science and data science tools that we had to use in here to accomplish this. But I think the essential part that I'd like to tell you is, just as a matter of fact, everything we did there was implemented in Python. So Python was our framework for implementing this model. And there may come up the question, okay, now you're having this AI model, how does the user work with this? And what we did for that is we also implemented a REST API, also Python-based, inside of the cloud infrastructure of our client. And this was very handy because there were two different possibilities. So either they can use the user interface, go into this REST API and upload documents, get the result, get the classes for it, or it's still a REST API. It can be requested from any software or tool that's inside of the BASF infrastructure, so they could also connect it quite easily to other tools, and that's also how it's working in the end. And yes, so I think with this I'm done. I know I talked quite fast because I wanted to give you as much information as possible in this 15 minutes, but if there are any questions left, please let me know, and besides that, thank you a lot for your attention.
Have to share the mic now. Thanks. Yes. So we have 5 minutes for questions. Are there any questions in the room? No. First, before we do questions, I just give a short announcement. How to do questions? In the room, just raise your hand. Then Christoph, he's the guy in the green T-shirt. He will come to you with the mic, and you can post your questions online. Lukas is over there. He's our online chat manager, and he will gather the questions from the online chat and then just read them out loud. So you can post the questions online or in the room. Good. Oh, okay.
Thank you. Hello, I'm Micha from Lab Research. I just have a question regarding the consequences or costs of a false classification. So what is the problem if you classify a document in the wrong tag?
Okay, so what's basically happening if you're so I cannot give you a number in euros in that case, but what's basically happening, so if you classify it wrong, these wrong tags are of course also in their data warehouse, they are stored there. So what's happening is you're having some document with wrong tags. But what's also happening, and maybe important to note, sometimes these tags are not unique, so there is some sort of gray zone, is this Grauzone? You know what I mean by Grauzone, okay? Where it's also okay if a document is classified in one or the other class. So it's not that bad, but it should be reduced as much as possible just because of data quality.
Thank you very much for the interesting talk. I'm Natalie, I'm simply a PhD student. I was interested, if it is not confidential or anything, then how often do the data afterwards, the data are classified by the tags, are accessed by the users? So, like, for which reasons do they use this? Like, how important it is?
Okay, actually that's very simple to answer. It's used in a search engine, so it's quite often that you really need those tags. So you need this information to easier find the documents you need when searching for them. So it's used really on a regular basis.
For a particular documentation process.
Exactly.
Sorry, we just need, for the live stream, we need to repeat the question in the mic, please. Or a man.
So it was for data documentation purposes.
Exactly, yes.
Now I have a mic. I have also a mic. Sorry for that. We have an online question, just to get used to all these settings here. An online question from the chat.
Yes. Arash asks what the kappa parameter in your results slide was.
Okay, the kappa parameter is just another metric to see how good your results are. What the kappa basically does, it compares it with a random classifier. And if it's between, I think it's 0.8 and 1, you can say it's a really good classification result. Just the second metric, because accuracy is sometimes discussed, let's put it that way, if it's the right one to choose.
We just got another question online as well, if we have time. Andreas asks, which kind of ANN algorithm did you use? And if you can give a comparison about the accuracy between different models.
I can give a comparison. So can we which kind of what algorithm?
ANN. I don't know what the A stands for, some kind of neural
Awesome.
network.
We didn't use them at all because it wasn't necessary. So we just stopped at support vector machines. So actually, one of my colleagues started to look at neural networks, but the first tries weren't that good. So we reached accuracies around, as far as I remember, 70% or something like that. And I wouldn't say that they're not working, because if you put some time and effort in it to really work on them and tune them, they would probably be great. But as it's mostly the case, time's a very limited resource inside of the project, so that's why we stick to our support vector machines. And for the naive Bayes, I think it was around 60%, so it really did not work at all. Probably the reason for that was that the classes were quite imbalanced, and as far as I remember, it's something that naive Bayes cannot really work with that well.
Okay, we have one last question. Yes?
Hello, it's Martin speaking from Kai. Thank you very much for this interesting talk. I thought about the slide of your methods here, and you have said the naive Bayes, the support vector machine, and there was a neural network approach. Did you compare it to the support vector machine approach in some way? Because nowadays it's a hype, so artificial intelligence with neural networks, artificial intelligence. Did you compare somehow results with deep learning approaches?
So basically it's the same question.
It's somehow similar to this question before, of course. Neural network is a quite diverse field, I would say.
Yes, exactly.
Did you go deeper in this field?
No, we didn't. It was really like, I would say, a scratching on the surface.
Okay. Thank you very much.
Thanks a lot. Thanks again to Natalie.
Thanks
for a great talk.